Hey guys, this video is going to be about solubility equilibria, so let's get started. Alright, so remember the solubility rules that we had to memorize a long time ago? And these right here were strong electrolytes, if they dissolved completely, electrolytes, and these were weak electrolytes. And we used the equilibrium arrows to show that. Well, we're going to talk about how they're in equilibrium and how they're related to each other. So if they're insoluble according to solubility rules, that doesn't necessarily mean that they're insoluble. That means that they're marginally to partially soluble. So the solubility product constant is another K, and we call it KSP. And so the KSP just shows the relationship of the dissociation of a salt that is considered to be insoluble. So with silver chloride, we know that that's an insoluble salt. It's marginally soluble. And the relationship would be between silver ions and chloride ions raised to the first power, because there's only one of them each. And then we don't put silver chloride in it at all because it's a solid, and solids don't go in equilibrium expressions. So technically, these equilibrium calculations are going to be easier than the ones we did in the past, a few units back. And that's simply because this will never have a denominator in it. To get us started, a couple of examples. We have silver acetate, and even though acetates are generally considered to be soluble, silver does some strange things to stuff, and so this has a KSP associated with it, and so we can write an expression with it. So if we have silver and acetate, there's only one of these and one of these here. Both are +1 and -1, so that would be the dissociation reaction, and then the KSP would be equal to silver and acetate, and there would be nothing in the bottom because this right here is a solid. Remember, ions are always going to be aqueous. B is aluminum hydroxide, and it dissociates to form an aluminum ion, which has a +3 charge, and 3 hydroxides because there are 3 of them. And so our KSP will be equal to the concentration of aluminum times the concentration of hydroxide raised to the 3rd power, because there's 3, right? So it's always raised to the coefficients. I know it's been a while because we've been in acids and bases, so you don't see that very much with the acid-base stuff, but don't forget about it. And the last one is calcium phosphate, and calcium has a +2 charge. Phosphate has a -3 charge. That's where these came from. And we have 3 calciums and 2 phosphates. So then the KSP expression would be calcium to the 3rd power and phosphate to the 2nd power. Okay, so if we have a saturated solution of calcium fluoride that's in contact with solid calcium fluoride, it will contain constant equilibrium concentrations of both the calcium ions and the fluoride ions, because at equilibrium, the ions crystallize at the same rate as the solid dissolves. So let's look at a picture of what that would look like. So if this right here, this white stuff, is our calcium fluoride, and we look at it at a molecular level, we would see something like this. So we've got the little green ones are the calcium ions, and then the yellow ones are the fluoride ions. And so this is the white stuff in the bottom of this flask, right? And you can see that it's a solid because they're all packed closely together, and it's in equilibrium with these ions. A few of them break off and go into solution, and so that shows how soluble that salt is. And then we can calculate the KSP for that by plugging in the concentration of the calcium ions that are free and the concentration of the fluoride ions that are free and squaring it. And that would give us our KSP. All right, so here's some KSP values for some ionic compounds at 25 degrees Celsius. And as you can tell, they vary greatly, and some of them are very, very insoluble. So the lower the KSP means that it's less soluble. It also depends on how many particles are dissociating, but for the most part, you can tell what's most soluble. So these right here with 10 to the -5 are going to be more soluble than something with 10 to the -33rd. All right, because that means if it has such a small K, it doesn't go forward well. So if the reaction doesn't move forward well, then it doesn't produce a lot of product. And remember, the ions are the product. We're going to calculate solubility. Usually we calculate it in molarity. Sometimes they'll ask for grams per liter. I typically just ask for molarity, but it's not necessarily uncommon to see grams per liter. And most of the time in textbooks, they make it look like something new. They don't make it look like what you've been using, rice tables. So I'm going to kind of use a rice table and then start slowly moving away from it, but I'll always tell you what I'm doing. Okay, so for the first one, for A, I want to find the solubility, and the solubility is just X from the rice table. And sometimes they use the letter S, sometimes they use a capital S, sometimes a lowercase. They change it. It just depends on textbook to textbook, but I'm just going to use X. So in A, I've got lead 2 iodide, and it will dissociate into lead ions and iodine ions, and we'll get 2 iodide ions for every lead. And so my KSP for that will be equal to lead 2 and iodide squared. And it says that the KSP is equal to 1.4 times 10 to the negative 8. That is not the solubility. That's the K. So we're looking for the X. So when we first do this using a rice table, remember solids, we don't include those in the rice tables because they're not in the K, so they're not going to help us. And starting out, we don't have any of this because we just put a bunch of solid into water, basically. So the change here, this is going to go up by X, and this will go up by 2X because there's twice as many. So every time we get one of these here, right, we have to get 2 of these here. So this is going to be X, and this will be 2X. And then I'm just going to plug my equilibrium values into my KSP. So what I'm going to end up getting is that my KSP, which is 1.4 times 10 to the negative 8th, is equal to X, because that's the lead, right? So it's going right here. X times 2X will go into this one, and we're going to square it. So if I simplify that, I get X times 4X squared, because I have to square everything inside of the parentheses, so that 2 has to get squared. That's a common place to make a mistake. And that's going to be equal to 1.4 times 10 to the negative 8th. And then further simplify, I get 4x cubed is equal to 1.4 times 10 to the negative 8th. So divide both by 4. And I end up getting 3.5 times 10 to the negative 5th. And that's equal to x cubed. And then to undo a cubed root, instead of going through the menus in your calculator, I just raise it to the 1/3, so it'll cancel out that 3. And my x value ends up being 0.0327. Okay, so that's my solubility. And what that means, I'm going to write this in red. What that means is that 0.0327 moles of lead 2 iodide will dissolve in 1 liter of water. That's what that means. So my concentration of lead 2 would be 0.0327 molar in a saturated solution. It has to be, it's completely saturated, no more can dissolve, right? And iodide would be twice that because it'd be 2x. So that would be 0.0654 molar in a saturated solution, because it's twice as much as this one would be in that solution. All right, so now I'm going to do the next one. I'm going to do B. So I have cadmium carbonate, and it dissociates into cadmium ions and carbonate ions. Remember, that's a solid. And so my KSP for that will be cadmium and carbonate. And initially I'll have 0 of this. This doesn't matter. And so the change will be plus X and plus X. So at equilibrium I have X and X. So remember, if you have 1 and 1, it's pretty straightforward. It's X and X. So then I would have X times x is equal to 5.2 times 10 to the negative 12. So then I have x squared is equal to 5.2 times 10 to the negative 12. So if I take the square root, I find that my solubility is going to be 2.3 times 10 to the negative 6. So 2.3 times 10 to the negative 6 moles of cadmium carbonate will dissolve in 1 liter, which means in a saturated solution, I would have 2.3 times 10 to the negative 6 molar cadmium, and I would also have 2.3 times 10 to the negative 6 molar carbonate. All right, now part C, for strontium phosphate, solid, we have strontium, which is going to have a +2 charge, and we have phosphate, which is going to have a -3 charge, so that's 2 and 3 of those. So my KSP for that is going to be equal to strontium cubed and phosphate, I'm running out of room, squared. All right, and then for a rice table, the solid doesn't matter. These aqueous things do. I have 0 of this and 0 of this. So this will be plus 3x. So we have 3x. And this will be plus 2x. So that would be 2x. And so then I'm going to plug these into here and plug in my KSP, which is 1 times 10 to the negative 31, will be equal to 3x cubed and 2x squared. So 3 cubed is 27x cubed, and 2x squared is going to be 4x squared, because you have to square the numbers inside the parentheses and cube the numbers inside the parentheses. So then I'm going to multiply the two numbers. So 27 times 4 is 108. And then x to the third times x squared is x to the fifth. And then divide by 108 on both sides. And I get that x to the fifth will be equal to 9.26 times 10 to the negative 34. And then I'm going to raise both sides to the 1/5. That gets rid of that. So then my x is equal to 2.5 times 10 to the negative 7 molar. So that would be my solubility. That would be the answer that they're looking for. But I wanted to also put out there that since this is times 3x, right? That the concentration of strontium in a saturated solution would then be this times 3, which is going to be 7.5 times 10 to the negative 7. And then phosphate would be times 2, so it'd be 5.0 times 10 to the negative 7 molar. All right, now this wouldn't be part of the answer, but it'll help you understand it if I keep calculating it. All right, so this is different, it's backwards. We're going to calculate the KSP for lead 2 phosphate, and this time we're given the solubility. So this is X, and we want to find the KSP. So I'm going to go ahead and write my reaction, and that's one of those things that I suggest you do even if it's not asked of you. Now on the AP test, they usually give those to you now, so you don't really have to worry about it, but you know. So instead of doing the whole rice table, I know that I'm going to end up with 3x here and 2x here, right? Because it's 0 plus 3x, and then you get 3x. So you end up getting that. So then I'm going to have in my KSP is going to be the KSP is equal to 3x, and then it has to be cubed, and then 2x, and it has to be cubed or squared. So I end up with 27x to the third, 4x to the second, so that's 108x to the fifth, and that will give us our KSP, which is what we're looking for. So now I can plug my x value in here, and I have 108 times 6.2 times 10 to the negative 12th raised to the fifth. So you have two options. You can either plug in your x value here, multiply by the 3 then, and then raise it to the third, plug in your x value here, multiply by 2, raise it to the second, and then multiply those two values together, or go ahead and find this, and then you'll raise it to the fifth first, and then multiply by 108. So if I raise it to the fifth, because you have to do exponents first, and then multiply, I get 9.89 times 10 to the negative 55. And so that's my KSP. And remember, KSPs do not have any units. Ks don't have any units. And just to be on the safe side, I'm going to write my expression as well. So this is a different kind of problem. It's very similar to the last one, but it's a little bit different. So we've got the silver concentration in a saturated solution is 2.2 times 10 to the negative 4. So this is the silver concentration, and we want to know what KSP is. So I'm going to write my reaction. So 2 silvers for every oxalate. This is a solid, and my KSP will be equal to the concentration of silver ions squared times the concentration of oxalate. All right, and so this is going to be 2x here, and this would be x, right? That's what we would end up getting. Well, I know that my silver concentration in the solution is 2.2 times 10 to the negative 4th. So that is 2x. So 2x is equal to 2.2 times 10 to the negative 4th, which means that my x value is equal to 1.1 times 10 to the negative 4th. So if I know that, then I can just plug these in because this is silver and this is oxalate. So I have 2.2 times 10 to the negative 4th squared times 1.1 times 10 to the negative 4th. And that would give me my KSP. So all I did was plug this in for silver and plug that in for oxalate into the expression, and I end up getting 5.3 times 10 to the negative 12th. All right, so what happens if we add something or change the pH? This can get a little weird sometimes, so pay attention. All right, so we have lead 2 iodide, and we're given the KSP for it as 1.4 times 10 to the negative 8. We want to calculate the solubility. And we want to calculate it first in water, then in 0.1 molar lead 2 nitrate, and then in 0.1 molar sodium iodide. So I'm going to write my reaction, and I'm also going to write the KSP. All right, and then I know that this is going to be x and this is going to be 2x. There's nothing in water that is going to affect this, so I'm just going to plug these in, and it's just a regular solubility calculation. So 1.4, this is A, 1.4 times 10 to the negative 8 will be equal to x times 2x squared. So that reduces down to 4x cubed. Divide by 4. That's 3.5 times 10 to the negative 9th. Take the cubed root, raise it to the 1/3 of both sides, and my x is 0.0015. All right, so that's in water. Now, B says we're going to have 0.1 molar lead 2 nitrate. So lead 2 nitrate, nitrates are always soluble no matter what. So this completely dissociates into lead 2 and 2 nitrates. Now, nitrate isn't going to affect this, but the lead will because it's part of this equilibrium over here. So if this goes up, it's going to shift back. And so what I'm assuming is going to happen is that the solubility will decrease because it's going against dissolving, right? It's going to form more solid. So when we do these calculations, instead of having x here, you're going to have the concentration that you're putting into it. So since I have 0.10 molar of the lead 2 nitrate, that means that I'm going to have 0.10 molar of lead 2, and I have 0.20 molar of nitrate, but the nitrate's not going to affect it. So we're only concerned about this. So I'm going to rewrite my reaction so that you guys can see what I'm doing here. All right, and instead of starting at 0, if we do a Rice table, I would start with 0.1 of that, and I still wouldn't have any of this. So my change is going to be plus x, and I end up with 0.10 plus x and 2x. So now I'm going to plug that into the KSP, and I have 0.10 plus x times 2x, and that's squared. Now this X, because these K's are so little, this X is negligible, just like in acids and bases. So this becomes fairly easy then. I end up with, if I collect like terms, I have 4, because 2 squared times 0.1, so that's 0.4 x squared is equal to 1.4 times 10 to the negative 8th. So I'm going to divide both sides by 0.4, and I get 3.5 times 10 to the negative 8th is equal to x squared, and then I'll take the square root of both sides, and my x ends up being 1.87 times 10 to the negative 4th. So if we compare these two numbers, this one is definitely smaller. The new one is definitely smaller than the old one, and that's because the equilibrium shifted to the left and caused it to dissociate less. All right, now part C is going to be very similar. The only difference is what is going to start off in our equilibrium thing. So I'm going to erase what I have here for B and rewrite it. Okay, so for part C, I've got sodium iodide, and alkali metals dissociate completely, so I get sodium ions and iodide ions. So if this is 0.1 starting out, then that means I have 0.1 of this, and I have 0.1 of this. So this is what's going to affect my equilibrium because it's part of it. So rewriting the reaction, and I have 0.1 of this starting out, none of this. This goes up by x, this goes up by 2x. So I have 0.10 plus 2x and x, and then I'm going to plug that into the equilibrium expression. So I have x times 0.10 plus 2x, and that would be equal to 1.4 times 10 to the negative 8th. So again, because we're adding something to this side, it should shift to the left and reduce the solubility. So this can cancel out. Oh, and this is squared. Don't forget to square it. So we have 0.1 squared, which is 0.01, times x is equal to 1.4 times 10 to the negative 8th. And then I'm going to divide both sides by 0.01. So I get 1.4 times 10 to the negative 6th. And so that reduced it a lot. And the reason it reduced it more is because it's going to affect K more, right? I mean, it's squared value. All right, so the easiest way to do this is if you're starting out with an amount, that goes in place. You can get rid of the x altogether. You don't have to go through all this rice table stuff. And then instead of having plus x here, right, you would just write x because there's only one of them. Or you'd write 2x if there's two of them. All right, so you didn't think you'd get away scot-free without having to mess with pH or anything anymore, did you? Because this one deals with that. So I'm going to have iron 3 hydroxide, and it will dissociate into iron 3 ions and 3 hydroxide ions. And my KSP for that will be 4 times 10 to the negative 38, so this doesn't dissolve very good at all. All right, now, because we have hydroxide, water is going to affect this. All right, in water, remember the hydroxide concentration in pure water is 1 times 10 to the negative 7th. So that means that this is going to be 1 times 10 to the negative 7th concentration. And iron will be just x. Then when we plug this in to our KSP expression, which is going to be iron 3 and then hydroxide cubed, this ends up going into this. Because you would be plus 3x, and then the 3x would end up being negligible. We could cancel it out because it being added to this is not going to affect it. So we have Fe3 is x, and 1 times 10 to the negative 7th cubed is equal to 4 times 10 to the negative 38. So I'm going to end up with 1 times 10 to the negative 21 times x, and then divide both sides by 1 times 10 to the negative 21. My x ends up being 4 times 10 to the negative 17. So if I was to add that number to 1 times 10 to the negative 7, it would not affect it. It's way, way smaller. All right, so B is in a buffered solution at pH 5. So at pH 5, where do I want to write this right here? pH equal to 5, the pOH is equal to 9. And so my hydroxide concentration is 1 times 10 to the negative 9th. Now, because this is less than water, 1 times 10 to the negative 7th, then we're actually reducing this. And so this should increase the solubility. So if you're producing a hydroxide and you make the solution acidic, it will eat up the hydroxide, forcing the salt to dissolve more. So if this is going to be X, and then this will be 1 times 10 to the negative 9th, we're going to do the same process we just did. All right, so I'm going to do B right here. So I've got 4 times 10 to the negative 38, my KSP. Fe3 plus will be X, and the hydroxide will be 1 times 10 to the negative 9th, but remember it has to be cubed, right, because that's what's in the KSP expression. So that would be X times 1 times 10 to the negative 27th, and then divide both sides by 1 times 10 to the negative 27th, and I end up getting that my X is equal to 4 times 10 to the negative 11, which is more soluble than it was before, right? This is the solubility here, and it's a bigger number. All right, and then part C, we have a solution buffered at pH 11. So at pH equal to 11, the pOH is equal to 3, and so my hydroxide concentration will be equal to 1 times 10 to the negative 3rd. And so instead of these values here, I'd have X for Fe3 plus again, and then 1 times 10 to the negative 3rd for hydroxide. So I'm going to plug that number in, and then 1 times 10 to the negative 3rd, be cubed. Don't forget the cube because it's in the expression. So that would be 1 times 10 to the negative 9th that I'm dividing by, and then my X will be equal to 4 times 10 to the negative 29th. So that reduced the solubility a lot, and that's because this is so much bigger than water. We're increasing this concentration, the reaction is shifting back towards that and decreasing the solubility. All right, so that's it. I know it was long. I'm sorry. I'll try not to ever do it again.